the target phones across the all aligned frames. And basically, it tried to give the score that is closest to the actual phones. And the LPR is the log posterior difference between the target and the competitors. So it provides the contrastive features other than just the top scores. So basically, we try to fuse these two features together, and hopefully the transformer can understand the difference between the top scores and also the contrastive scores together to give a better scoring. And we fuse these two features and add the phone identity tag, and we just use 24 and fuse it into a 24-dimensional projective sequence embeddings as the input for the transformer. And the architecture of our model, we compare several baselines, such as the linear regression, a shallow MLP model, which is only two hidden layers, and the vanilla transformer. And our proposed method also add the learnable position, because when you are trying to give a speech or just a speak utterance, and the position is quite important. And also we add an attention related. And for the training, we use the MSE as the objective function for regression. And for the 9 class classifiers, we just rounded into the 9 categories. And we found out that because the data we have from the Hakka console, and there are some data issues about the label school, because the teacher tend to give people middle scores rather than very high score or very low score. Okay, so that's the label school we have in our database. So that's why we find out that regression tends to preserve rank fidelity better than the classifier, and that's what intrigued us to add the post-processing, which is the bias calibration. And for our data and the model setup, for the alignment data, we use the Hakka ASR trained on like 280 hours of reading speech, and we use a tenth of it for evaluation. And we found out the phone error rate is about 5%. And for the scoring corpus, as we said before, it is a very small corpus, only have 20K read speech, and the score is between, the human scorer annotate the score between 0 to 4. And because we have 2 certified instructors, and the final score is the average of both instructors. And for our model, we use 80% for training, 10% for validation, which is used for bias calibration, and use 10% of data for the testing. And we report the metrics, minima square error, minima absolute error, and Pearson correlation coefficient. And for the discrete testing, we use 0.55 grid for rounding. So first, let's see the result for regression. In this table, we can see the result from vanilla model and the proposed model. Because the original table is quite large with other baseline, and we found out that basically the transformer outperformed the traditional method. So we just show the table of vanilla transformer and our proposed transformer. And this table, we compare the different features. And as we can see here, if we fuse the 2 features together, which is LPP and LPR together, we can get the best MSE and MAE. Also, we have like a 0.8 PCC. And for the discrete setup, the transformer classifier for the 9 class, although it have a slightly better accuracy, but in the core systems, the error and the PCC is much important compared to the accuracy. So we still use the regressor for our system. And for the post-processing, which is the bias calibration, we compare the global calibration and the per bin or per class calibration. And as we can see here, if we use the per bin post-process, and we can get the best PCC, which is almost 0.9. And we have also used some significant tests and find out this result is statistically significant. Okay, so for the practicality and the future work, since I don't have so many time, basically our model, our system is built on a lightweight transformer, and we also just use a single pass, so it is very practical, and it can give an instant feedback that if the student upload their practice sound, we can directly give it a sentence level score. And for the future work, because this is the post-process is very database driven, so we try to leverage like maybe something like SSO pre-training and also the articulatory feature attribute to help to further enhance the system. And maybe we can use, can provide some phone level result. Okay, so in our conclusion, we propose a lightweight transformer and use the fused GOP features and deliver a strong continuous scoring, use the post-processing, and which is a class-specific bias calibration, and it improves the MAE and the PCC, and it nears the teacher level scoring. And it is very practical for the low resource core system, and it is already, we are already applying to the class pilot study. Okay, thank you.
Thank you. So the floor is open for questions. Can we have some questions now? No question? Maybe I'll start. So I was wondering, like you talked about the ASR alignment. How good the ASR alignment is in comparison to like human, let's say annotators. Did you try measuring that?
We haven't tried to assess the measure the alignment accuracy, but we have report the phone level error rate is about 5%. So I think it's quite good.
Because a lot of cases your LPP would totally depend on how good the alignment is, right? And then when you're doing like this fuse of LPP and LPR, is that the reason that you're doing that fusion? So that if there is something that is not
actually, in our analysis, we found out that LPR is much useful than the LPP because it provides the contrastive scoring that can help model to recognize when the user have the good pronunciation or bad pronunciation.
Okay.
Yeah.
So I'll just ask if anybody else has a question. Yeah, there is a question at the back there. Can we have the mic there, please?
Yes. Thanks. Okay. Good. So good afternoon. So this is a scoring system for pronunciation. Yeah, but how do you? Also, the first question is it cross-prompt? It means that you use different prompt for for scoring the pronunciation, or this is uniprompt, but using the same data and then you split it data for training and test data. Yeah, this is the first questions. And the second questions, so how do you normalize the different system of scoring, or do you use only one scoring system, or do you use the real data that was collected by different teachers who have different method of scoring? Yeah, thank you.
Okay. So for the first question, that we use the data split for evaluate our system, because we have the Hakka Council provide us that their Hakka language exam that is annotated and maybe just scored by the real teacher. So I think the score is quite reliable. And our goal is that we provide help for the teacher that, or maybe this student have something wrong with her pronunciation, so we can give a quick feedback to the teacher, and teacher can check the score and to see if that is right or wrong. So we are not just give the score directly to the student, but just provide some suggestion for the teacher. So that's why we use the annotated corpus as our goal, to provide some suggestion. That's the first question. And the second question, you say that different score system, or we have compared to use different model, like linear regressor or just shallow model, and we find out the transformer because it can just input the entire sequence and to check each of the token and to see the token is aligned with the correct answer. So I think that's why it performed the best compared to other scorer in our testing. And because we have already further our test the system into the phone level, and we found out that the student feedback is quite good. So maybe when because we built a platform, and if we can collect more data, and maybe the teacher can give us some, maybe we have the system provide the wrong answer, and it can correct that. And after it correct that, our model can be retrained and fine-tuned to a better one. So it becomes a cycle and further enhance the system performance.
Thanks,
okay, thank you.
Huang Yichin, for your answers. Sorry, for the interest of time, we have to cut the discussion a little short. Thank you so much, and let's thank the presenter. May I request the next presenter, Lukita Fazri, to please present the paper. It's a joint paper. It's Hi-Fi Diff, two-stream diffusion models for high-fidelity speech generation of unseen languages. The floor is yours.
Okay, thank you, Professor Priyanko. So, my name is Fazri. I am from Indonesia. Today, I'm going to present our work entitled HiPi two-stream diffusion models for high-fidelity speech generation of unseen language. Actually, when we are talking about text-to-speech synthesis, actually, there are two models that consist built into the text-to-speech system. The first system is converts the model that converts from text into the acoustic picture, which is actually we can call it a MEL spectrogram. And then another model is that converts acoustic picture to the speech. I mean that the WAP frequency. So in this paper, we're focused in the vocoder. So this is the system, the model that converts from acoustic picture into the speech. Okay, so we are actually concerned about the vocoder, especially for deep web. So deep web is a speech generation or neural vocoder based on diffusion model. In the past year, we have seen that so many generation model, especially for speech that use generative exponential network. But in recent year, we see a model like diffusion model, which is very great in generating image. So this model partially converted and adapted into the generated for speech. So one of the best model, which is based on diffusion model, is deep web. So it can produce high fidelity speech condition on the acoustic picture, which is the MEL spectrogram. So the diffusion process is actually consists of two steps: the diffusion, the forward step, and then the reverse step. So in the diffusion process, it gradually adds small white noises to the data, which maybe we come with a speech, and then we add some noise. So it's called noising. So until we get at the end XT, which is speech that is full noisy. So the second step is the reverse process. So we define it is a step-by-step denoising of XT until it can back the original data. So the probability compared to, on the other hand, compared to the diffusion process, in these denoising steps, the probability distribution is parameterized. So what we're actually searching is for the parameter of the distribution of the denoising steps. So, however, there are some challenges of generating vocoder. I mean that we know that deep web is achieve state-of-the-art natural sounding speech. It means that it can result in some very high quality of speech. But the success is much relies on large and single language high resource data set like English. So this is because a problem because we have so many language in the world that is there are no data set with low resources, as mentioned by Professor Suyanto earlier in this speech, that there are actually more than 70,000 low resource language. So the problem is that when this model are used for unseen language, so I mean that we have the system that using zero-set synthesis, we train the model, the diffusion model, the deep web, using only the English language, and then we want to try the zero inference using that model on the low resource language. So the core issue is when this model used to import the language that doesn't unseen in the trained data, we have some significant speech inaccuracy. So this is a major problem and major barrier because we have so many language in other words that very lack of data set. So what we want to is here is the artifact that we capture. This is a MEL spectrogram. So this MEL spectrogram can be seen as the fingerprint of speech. So from the image we can see some valuable information. So after the deep web, so In the top left, we see the ground truth of a speech, and then in the second image is a deep web. So we can compare that both unpoised and sound and poised sound. There are some artifacts in the left corner. We set green, yellow block that a fundamental frequency, so F0, but in the deep web, they are absent of the fundamental frequency. But our approach, we call it hippie deep. We can actually matching the Mel spectrogram that is generated in the ground truth. So I mean that our approach can generate a similar spectrogram. So why the deep web fail? I mean that why the deep web fail when used to import the unseen language on the trained data. So our hypothesis is that the problem is the architecture that the deep web uses. So the speech is actually composed of two different signals. The first is poised sound, and the second is unpoised sound. So the unpoised sound is the sound like E, O, or maybe M. So, and the unpoised sound is a consonant. So the poised sound is quasi-parodic. So this is low frequency. On the other hand, the unpoised sound is a parodic, just like noise and have the high frequency. So the poised sound defines the pitch and melody of speech. On the other hand, unpoised sound defines the texture of the consonant. So the poised sound needs a wide receptive field, and the unpoised sound needs a narrow receptive field. So we propose that hippie deep, that is, we create a custom architecture, then tackle different poise using different architecture. So in this architecture, we separate between periodic signal and aperiodic signal. In the periodic signal, we tackle in using another. So it's, the hippie deep is consists of periodic stream. So the first stream is to model the poised sound. So this is a low frequency signal. This is a longer receptive field. So we use dilation to I mod attempt to capture. So I mean that this is to capture a very long signal, and this includes is a low pass filter. So we only allow a low pass frequency in this stream, and in the stream 2 is a periodic stream. This is specifically to model unpoised. So this is a high frequency signal. So this is use a shorter receptive field. Yeah. In the final step, we combine the output from both stream, and we combine them to predict the final speech. So this is the complete architecture that we use. So the architecture consists of the periodic stream and the aperiodic stream. The aperiodic and the aperiodic stream take the same input, but in the process, in the periodic stream use longer receptive field, but in the aperiodic stream use shorter receptive field. But at the end, in the output, we combine them, so it's become single output, single spectrogram. Okay, to give what is a dilated convolution, here is an illustration to get a better understanding about dilation convolution. So in the normal convolution, we actually get no holes, but in the dilated convolution, we get some hole to make the receptive field wider and longer. So we can use this technique to control the dependency of the engine. So in the system, we use longer receptive fields, but at the periodic stream, we have a short receptive field. So the training objective is actually diffusion-based model use a very beautiful error. So we train HippyDeep to minimize L1 loss. So between the target noise, epsilon, and the predicted noise. So we have a very beautiful equation here because compared to the GAN-based generator, which is a very complex error function, but in the deep web, we have a very beautiful and a very simple training objective. So actually, using this error objective, using this training objective, we can get stable training. So it's very, 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 very interesting. So we have composed the architecture and then conducted some experiments. So we have the training data using LG-SPIT. It's actually contains 13,000 scripts. But on the testing data, we have some language, actually 10 language, which is done unseen in the training data. So in the test data, actually, we have South African language, some language in the African, in the South African, and we also use Indonesian like Sunda, Balinese, Batak, and etc. So we train that model using the LG dataset, and then we test using the unseen language. So this is the hyperparameter that we use. So the result is that we can see that HippyDeep give some improvement from the deep web. So in the deep web is the deep web is trained also using English and then try to import using those language which is unseen in the training data. And also the HippyDeep they train using English language and then try to import in those languages. So in this setting, we have unseen language. So we can compare that HippyDeep have so many improvements to the deep web. So I mean that there are some limitations because we only use a single speaker training data using LG-SPIT, but maybe in the future what we can use trying on multi-speaker and multilingual data. And also we have very limited language diversity. So maybe, I mean that evaluation is not include a tonal language. We use a regular language, and maybe in the future world, we can use tests on the tonal and phonetically distant language. So I mean that the conclusion is that the problem is because the deep web produce pitch artifact, and our hypothesis is that the single resective fields is inappropriate to modeling both poised and unpoised sound. So our solution is an appeal two-stream diffusion model with separate periodic and aperiodic resective fields. So I mean that it's enough for me. Maybe we can continue to the Q&A.
Thank you so much. Round of applause for the speaker. Okay, can we take two very short questions because we don't have much time? So is there any question that we can take? No question? So then I can ask you from what I have in my mind. Okay. So you talked about the speech, I think, inaccuracy artifacts, right? So then what is actually are you targeting the tone aspect of that by that, or intonation, or just overall like naturalness of speech?
Yes, in the metric, we use overall pronunciation. So we don't use any metric especially for maybe pitch, but we have to evaluate using a general pronunciation quality.
Okay, and then another very curious, I was curious about the spectrograms that you have shown.
Yes.
You showed that one part which is voiceless, one part which looks voiceless but has fundamental frequency there.
Yes.
Which is like not represented.
Not exists in the...
What was that part actually? Was it a phoneme part or it's a breath? or what was it?
Yes, the artifact is live in both in poised segment and the unpoised segment. So I mean that the bit in the hippie deep, when it generates the speed, we then evaluate the spectrogram. That spectrogram in the poised segment, there are no frequency. I mean that there are no some pitch inaccuracy between the ground truth. So yes, this is about the frequency, fundamental frequency, which is speed.
Okay, okay. Good. So if any other, yes, please.
Yeah, thank you for the presentation. I have a question for your experience setup. So for your metrics, you use MOS, but it's not a human evaluation, it's from model, right?
Yes, we actually evaluate our work using automatically most because limited technication because we have so many languages to evaluate. So to make this simple, we actually using automatic most mean opinion score. This is a metric which is using a machine learning model which is trained using actually using English, and then after it's trained, we can generate, it get input speech, then it can generate the most automatic most. I mean that approximate most.
Yeah, I see. So for your most model, you also training the many language, right?
No, I don't training on many languages. I was training only using English, but for simplicity, we use it to evaluate our results.
I see. So for your result, I feel it's very the Java and the Bali, only Java and the Bali language is the most score is very high, is around 4.2 and 3.9. But for the other, it's around 3.5. So
yes,
that is why I'm kind of curious. Why only Java is arrive so high score?
Yes, I think maybe because the most is actually trying using English language, so maybe there was some accuracy on the most metric. So I mean that we can use another metric that is appropriate using. Actually, for the better result, we can get actual most. We have maybe for each language we must provide a real person to evaluate it.
I will have to use my discretionary power as the chair now. It's an interesting conversation, but we'll take it off during the coffee time. Thanks for your question. Yeah. Thank you so much.
Thank you, Professor.
So the next presentation is going to be online. So it is Yukako, Katsuhiro, Sudo, Satoshi Nakamura, and Sakriani Sakti, bridging disfluent to fluent in speech translation, effective tagging, and fine-tuning strategies. So maybe if we have the video feed ready. Okay, I think I can see Yukako trying to present there. Can you hear us? Hello? Is it okay? No, I think she is a bit lost now.
Hello. Hello.
Yeah.
Hello. Hello.
I think she's. Yeah. Yukako, could you just say something so that we can confirm we can hear you? I think we are able to hear you. Yes. If you could be a bit louder, then that would be nice. Yeah. Now we cannot hear you. One sec. Now we cannot hear you. The feed is not coming, I guess. Okay, I have to stop talking only, then you can talk probably. So let me try this.
Thank you. Can you hear me? So let me continue the presentation. Yeah, if you have some trouble, feel free to let me know. Yeah. Thank you for your listening, everyone. My name is Yukako from NICE. So today I'd like to talk about...
We are not able to hear you. Just hold on a second, please. Okay.
How about for now?
Just hold on a second, please. So we are trying to figure it out here because your voice is not audible. It may be a problem with our system here, so just give us a minute.
Thank you. Yeah.
Check. Check.
Hello.
Yeah, we can partially hear you. Just wait for a second. Can you just say again?
Hello.
Yeah, can you increase the volume here, please? Output volume. Yeah, can you please test the mic one more time?
Hello.
Yes, it's perfect. So
Is
you can
this
start
voice
now.
is okay?
Yeah, now we can all hear you. Can you hear us?
Oh, thank you, Sakti Sensei. Yeah. So, yeah, if you are okay, I would like to continue the presentation. Thank you for your very many time. Sorry. Yeah, thank you. Let me talk about my research. This is what I was doing in NICE in Japan. The research is about different to fluent speech translation. Wait. So speech translation is the task that converts source speech to target text or speech. So these days, those kinds of applications for ST is widely used for travel assistance, simultaneous lecture translations, or movie subtitles like that. So yeah, it is very crucial for overcoming language barriers these days. So there are some challenges in speech translation. One challenge is that when the model has to treat the spontaneous speech, because the spontaneous speech includes some disfluencies like fillers or hesitations, that makes difficult for model, and the model degrades the performance in translation and gets the low readability. So fluent translation is better in this situation when we want more readability or usability and effective information delivery. So our target in this work is the task for our target in this work is different to fluent ST task to convey the summarized information without redundant different parts. So then, about DITS FST, one of the challenges is that we can collect only small size of data with explicit differential annotation. So generally, general fine-tuning for ST is in general fine-tuning ST, we have to prepare the large size of parallel data. However, there are only small size data in DCF data. So one research question is that how to run these fluent translations even with limited DCF data in end-to-end ST. So general cascade ST, when the cascade ST system have to treat these fluencies, one approach is preparing these fluency removal modules. So in Cascade ST, it is possible to prepare the explicit disfluency removal modules, but it is not possible in end-to-end ST because there is no explicit ASR modules, and it's not possible to prepare the explicit removal module after ASR output. So in our motivation is to apply this motivation to apply this tagging approach for end-to-end DCF ST. So our motivation, our approach is to mitigate the data scarcity problem in different to fluent speech translation. We have two approaches. One approach is tag-based augmentation. that is using augmented data through explicit difference tagging. The other approach is to to use those kinds of data effectively. We also want to apply the multi-stage fine-tuning with limited data. So this work was motivated by one work that was by Hori et al. They proposed to train the ASR models with difference tags to recognize differences. Yeah, they used filler tags or stammering explicit tagging approach to improve the difference speech recognition. So the different part between them is that we apply this approach for target text difference for a ST task. So before we move to the proposed model, we would like to talk about what kinds of data setting we are using. In this work, for example, the example data is Fisher Spanish corpus. That is one of the Spanish speech to English text spontaneous speech corpus. So there are original data, two kinds of original data. One is different to different setting, the other is different to fluent setting. We call them as D2D and D2F in this work. So when we apply the general fine-tuning for ST, we can train the model, first of all, with D2D data, and secondly, we can use the D2F data for further fine-tuning. So final trained model is D2D plus D2F data, D2F model. So note that there are no explicit difference tags in these original data. So there are such backgrounds that there are no annotations in original data. First of all, we propose to apply the difference annotator. We propose to prepare the difference annotated data using difference detector. So in this work, we can prepare two kinds of data with annotation. First is this D2D org tag data. The other is D2D org remove tag data. The only different part is that's the model, the data with tag or without tags. So these data are each motivated by tag data is motivated for identifying differences, and the remove tag data is motivated for removing differences task. So first step, we propose to prepare the tag-based augmented data. Not only that data preparation, but also we also want to leverage and use those kinds of data effectively. We propose to apply the multi-stage fine-tuning using those kinds of data. So in multi-stage fine-tuning, we not only use the augmented data, but also using the original data. So we will use fine-tune the from D2D to D2F with the augmented data. So in this fine-tuning flow, our motivation is to make the model that can identify differences or removing differences. So this is the experimental settings. We used the pre-trained ST model at Hubert plus Mbert pre-trained ST models, and we applied the fine-tuning for them. And as a data set, we used the Fisher Spanish corpus, both kinds of corpus. That domain is spontaneous telephone speech translation data. That input is Spanish speech and the output is target text in English. So we also prepare the two kinds of evaluation data. One is DCF test data. The other is some sampled data from DCF test data. It's called FD2F test data. So the motivation why we prepare the second data is that we also want to focus on the ideal cases where the difference should decrease in DCF task. So the samples are samples in this formula. So in the evaluation metrics, we not only use the blue scores, but also we have compared the difference ratios. So here is the main result. So from these results, we can see that from M4 to M6, those kinds of proposed method shows the higher blue scores and smaller difference ratios compared to M3 baseline models. So and when we see the M4 and M6, the scores, blue scores were almost the same, but when we see overall result, M6 is better to get the smaller difference ratios. So we see that M6 has the ability to eliminate the differences aggressively. So from these kinds of results, we can show that the effectiveness of combination of tag-based augmentation and multi-stage fine-tuning. Yeah, so this is one of the example sentence, and we show that this result shows that with tagging approach, before the tagging approach, there was the repetition was remained even after the DCF fine-tuning. However, in the proposed method, the tagging approach can assign the tags in the appropriate places, and finally, the difference number was reduced, and the translation quality becomes better. So this work, we proposed tag-based augmentation and multi-stage fine-tuning. And finally, we show the highlight of the effectiveness of those both approaches for difference tagging. Yeah, that's all from me. Thank you.
Thank you so much. So the house is now open for very quick 2 questions. Yeah.
Okay, that's okay. Thank you. So, if I'm not mistaken, the tagging process is applied to the text form, not to the speech. Is that right? The tag disfluency, the tagging of the disfluency or fluent, if I'm not mistaken, it is applied to the text form, not on the speech form. Is that right?
So the question is that the tag is applied to the text.
Yes.
and not to that speech. Is it
Speech.
correct?
Yeah.
Hello, can you hear me?
Yes, we can hear you. Yeah, so the question is, there is a question which wants a confirmation first, that the tag that you put is on the text, but not on the speech. Is it correct? Are you able to hear my question? That is. Hello. Can we? Yeah, hi. Are you able to hear me now? No? Yeah, hi. Can you hear me? I'm sorry, I don't think the two-way communication is working at this point of time. Maybe if anybody else. Oh. Sorry, you're typing? Okay. Yeah. Okay, is there any other quick question or? Yeah. If not, then, so, yeah, okay. Maybe we can conclude this talk then? Okay, I'm sorry. We are sending the question to her and then probably she'll get back to you about it. Okay? Thank you so much. Sorry, Yukako, I'm sorry that we are not able to communicate very well. So thank you so much for your presentation, and then we'll go to the next presentation for the matter. Thank you. Okay, can we cut the video feed and then go to the next talk, please? Can you cut the video feed, please? Can you ask them to cut the video feed? Thanks. Okay, so the next talk is Devansh Kapoor, Sania Setia, Shivam Arora, and Komal Bharati, Farm Sathi. Oh, yes. Okay. So the next talk is Farm Sathi, a retrieval re-ranking RAG framework for multilingual conversational AI in Indian agriculture. Until the next speaker comes online, I'd just like to inform that this session is actually up till 1450. So in case, like, you're wondering with one of the earlier programs, so the program has been revised and this session is up till 1450. Hello, Devansh. Are you able to hear me? Devansh? Hello.
Hello,
Hello.
hello, hello. Am I audible?
Yeah, yeah. Devansh, Devansh, hold on a moment. We'll just switch on the audio.
Okay, sir.
Can you?
No, sir, I cannot hear you. Uh, so am I audible, sir? Okay. S- Okay, so let me start. Just a second. So, good afternoon, everyone. My name is Devansh Kapoor. I'm a final year. I'm a final year Bachelor's of Engineering student at Thapar Institute of Engineering and Technology, India. So today I'm excited to present our paper Farm Sathi, a retrieval re-ranking RAG framework for multilingual AI conversation in the Indian architecture. The work is a collaborative effort of me and my co-authors Sanya Setia, Shivam Arora, and Dr. Komal Bharti. So let's not waste much time and jump straight into the paper. So in India, with such a large country having 121 major languages and 22 officially recognized languages, we are facing a critical language and information gap because half of the population of India is dependent on agriculture. Yet the farmers face a significant barriers while trying to access this information regarding to the agriculture. What are these barriers and why this gap is faced by the farmers is mainly because of the existing solutions and the languages that the solutions are available in. Most of the digital content nowadays is available, readily available in English and also in Hindi to some extent. But combining Hindi and English, only about half of the population in India will be able accessible to all the people in India so that they are up to date what's going on. There are existing solutions like PM Kisan, SMS alert systems, and chatbot, but they lack specificity because they are not fine-tuned with the dialects that many farmers speak, and they have a very high latency, and most of them are to the state chatbot and not audio bot, so there is no audio support. So coming on to the related work, there are many digital tools in conversation AI and agriculture, like the Enam and the Kisan Suvidha available. But yeah, the voice should be the ideal medium. But yes, the ideal medium in these mediums is the text, the chatbots. Uh, Coming on to the related works, there has been a lot of advancement in the field of RAG lately because RAG is becoming a state-of-the-art model with a lot of new innovations coming in the field, like the retrieval re-ranking and all. And it has actually bring down the latency of the RAG and also increasing the recall, which is a major factor in deciding the outcome of the situation. Third is the speech recognition tool for the low research languages. Uh, this is one of the major challenges in the country like India, where we have a lot of languages, a lot of different dialects, and a specific vocabulary for each domain. So a domain-specific ASR system is much needed, and there has not been much effort in this field. So that's what the research that we did aimed at. So let's start with the overall architecture. So our goal was to devise or make a multi-stage pipeline to optimize the trade between the accuracy and speed. Because accuracy in the fields like agriculture, where the knowledge is very field specific and critical, is very important. At the same time, we also need high speed systems because if the latency is too much, it's not be very usable in the real life scenario. So this is the pipeline that we tested and uh, find out to be the most optimal. Like we use a multilingual ASR processing firstly by doing feature extraction and normalizing the audio. The second step was fine tuning of ASR model. So we required a data set. For this, there were the data sets of All India Radio for the agricultural queries that we used. I'll come to this topic later. Firstly, I'll give a brief overview of the entire pipeline. Next came the query normalization, and after this, there was a retrieval re-ranking system. That is, we needed a fast retrieval, like we actually selected the top 10 candidates, which can be actual contenders of the documents, and and from these 10 documents, we did a precision re-ranking. All this is done in two stages in order to reduce the latency while preserving the accuracy of the model. The final output is fed into a LLM, or you can say a core of the RAG, which process it and gives us the final output, which can be converted back to the speech and the audio output. So let's go to each of this pipeline one by one. Like I have talked before, the data that the model will be outputting will be the agricultural data from the government website. It's dynamic in nature. So, like, if there is a new scheme of the government which has came recently, the model is up to date with that information. Uh, for the OpenAI Whisper-based model that we fine-tuned, the data set we used was from the All India Radio. There was a podcast that used to happen where they used to answer the agricultural queries in the regional languages. So we had the speech recordings of these, and this data gave us the domain-specific agricultural speech data that we needed in Hindi and Punjabi languages. So, quickly uh, going over to the stage one of a retrieval re-ranking RAG. It's the fast retrieval. Firstly, we need to actually find the top 10 candidates of the documents that can have the information that the person is requiring. So, for that, we use a model which is known as a bi-encoder. What bi-encoder does is it uh, makes embeddings and gives us thus top 10 semantically similar candidates. This model has a very high re response time, that is the latency is low, but the accuracy not that much. So that's why we have a stage two, which is precision re-ranking. It uses a model which is known as cross encoder. Uh, what a cross encoder does is it takes the top 10 candidates and it performs a deep token level search to find the top three highly relevant documents. So combining these bi-encoder and cross encoder, we get the very relevant documents, the top three documents. Uh, we'll come to the metrics later. Uh, After the context, that is these top three ranked documents are uh, fetched, these are combined into a clean single context which will be fed to the LLM for the generation. So the LLM we use was the Gamma 2-bit IT. It's a 4-bit quantized model. So the quantization did help with the latency as well, reducing the latency. And yeah, because the domain is very strict, so we had a very strict rule given to the LLM to avoid the problem of hallucination. Because uh, what these models tend to do is they'll be giving a response whether that's accurate or not. So in order to avoid the hallucination, context grounding prompt was given to the LLM, and the final output was processed into the speech and given back. Now coming on to the key results that we have achieved. The precision at 3 score was 87%. That means all of the top three documents that we fetched, 87% were very accurate and were according to the domain. We have to understand the point here, like the official documents that the government have put the curriculums, the schemes, they are very messy and not always conveying a single theme. They might have a wide variety of themes and not be very straightforward. So yeah, the precision at 3 of 87% was really good in this domain of agriculture with the government schemes. Coming on to the ASR performance of our model, the word error rate that we achieved was of 11.3% in Hindi, uh, which is a significant improvement to the earlier works done in the same field. And this proves that a domain adaptation and the retrieval retraining strategy was successful. Now coming on to the ablation study of the retrieval re-ranking. The retrieval only, the RAG only uh, precision at the 3 was 65% and the retriever plus re-ranker was 87%. In concluding that ranking stage is critical and it provides a massive boost in precision while maintaining low latency. Just a second. So, yeah, coming on to the conclusion of the paper, in this paper, we have introduced effective pipeline for a multilingual agricultural specific audio bot, uh, which is tailored to the Indian dialects and the regional languages spoken by the Indian farmers. We have employed a two-stage retriever re-rankle funnel, achieving a word error rate of 11.8% and a precision at 3 score of 87%. The re-ranker module and the pipeline was validated when we tested it in simple rag and thus supporting the studies and the research we made. So yeah, that was something from my side. If anyone has any questions.
Okay, thank you, Devansh. Do you have any questions for this paper? Devansh, you are able to hear us. If you can hear us, just thumbs up. Yeah, okay, I can see you nodding. Okay, so any questions? So maybe I'll ask you a very quick question about the data that you have collected, the All India Radio podcasts that you talk about. So you got both text data and speech data from that, I'm guessing. Am I correct in that? Is that the annotation already available, or you generated the annotation from the speech? Just hold on a second. We cannot hear you. So can you repeat?
Yes, sir. So the annotations were actually already available. So that was a huge plus point. Plus the data was very domain specific pertaining to only the agricultural queries. So the model uh, was actually able to learn the nuances of the agricultural term of the local languages. So yeah, that was a plus point with the data set.
Okay, so no further processing was required, neither for the text nor for the audio. Am I correct?
No, sir, there was definitely processing that was done. There was frequency normalization that we did. We applied a band pass, like allowing certain frequency to filter out the noise because the radio recordings were actually very noisy because that predated back, I guess, 30 years back. So the audio was not very clear. So yeah, a lot of pre-processing has to be done in the audio part, yeah.
Okay, thanks. Is there any other question that I can have? Yes, there is one question. Just hang on for a minute, okay?
Okay, so I saw in your presentation in indexing, you use Far East Index L2. As far as I know, Index L2 work using brute force. So how is the speed to retrieve on the performance on the speed when you use Far East Index L2? Thank you.
the latency increased a little bit using the file syntax L2, as yeah, you pointed out correctly. But it was manageable because of the whole retriever re-ranker architecture, the cross encoder that we used. So yeah, in the long run, in the big picture, the latency was manageable.
Hello? Okay. So any other question? Yeah. If not, thank you, Devansh, and thanks for your presentation. Yeah, with this, we come to the end of this session. So thanks to all the speakers and participants on this of this session, and I hand it over to the organizers now.
Check. Yeah, ladies and gentlemen, so that concludes our second oral session. We would like to thank our session chair, Professor Priyanko Sama, as well as all presenters here, and also Ms. Yuka and Mr. Devans that join us through Zoom. So thank you so much for the insightful presentation. And we would also like to apologize for the technical problems consist here, and we will now proceed to the poster session. We kindly invite all the poster presenters to stand by next to the posters. And before I call the name of the presenters, please allow me to apologize in advance for any possible mispronunciation of names. So the first poster will be presented by Jia Jing and Wen Chao, a study on Chinese tone and intonation errors among Bangladeshi learners, an investigation based on monosyllabic words and sentences. The second poster will be presented by Miat Ai Aung, Win Papa, and Sakriani Sakti, joining diarization and multi-speaker automatic speech recognition with overlap handling for long conversation. And the third poster will be presented by Chen Tianyi, Kuo Chun Chung, Lan Yuxiang, Lian Yuanfu, Chen Bowei, Liu Yi, and Wu Ming Xuan, rapid model adaptation of code switching ASR in low resource, high noise industrial domains. And the fourth poster will be presented by Doni Sumito Sukiswo, Hammam Riza, Muhammad Subianto, Taufik Fuadi Abidin, and Afnan, development of Aceh X for sentiment analysis using a BERT-based models. The fifth poster will be presented by Rubino PCY and Priyanko Sarma, voiceless laterals in HMAR. The sixth poster will be presented by Edia Saki Naufal Ilman, Desi Puji Lestari, and Candy Olivia Mawalim, entitled Enhancing Indonesian Deepfake Speech Localization with Pathological Features. The seventh poster will be presented by Bagas Aryo Seto, Nur Ahmadi, and Desi Puji Lestari, comparative evaluation of N-gram and transformer-based language model for ECOG-based speech neuroprosthesis. And the eighth poster will be presented by Nozomi Kuma, Gulabja, and Rubino PCY, Tokyo type accent production among the Northeast Indian students. And the ninth poster will be presented by Parismita Gogoi, Sisir Kalita, Priyanko Sarma, and S.R. Mahadeva Prasana, entitled Exploring Rhythm Format Analysis for Indic Language Classification. And the last one, the 10th poster, will be presented by Ade Rohman Maulana, Ari Ardianti Suryani, and Emma Rahmawati, entitled Lympho Less is More Approach for Visual Reasoning in Knowledge-Based Visual Question Answering. So we kindly invite all presenters to stand by next to the poster there in the back of our venue. And as the posters are displayed among the stairs area, please watch your step and be careful where you're going up and down. So we would like to invite all presenters to stand by next to the poster, please. Yeah. you can stand by next to your poster. And once everyone is ready, once the presenter is ready there, we will have 60 minutes, so 1 hour until 3:50. Yeah, until 3:50 for you to walk around and view the posters and interact directly with the presenters. The poster session will start now and end at 3:50. Okay, time is yours. All participants, please go to the poster and interact with presenters. Time is yours.
Check, 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 check.
Tick, tick, law, 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 tick, 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 law, law, tick, tick, tick. Oh, sorry. Monitor outputnya di sini belum dibuka. Udah. Cek, cek. Udah. Coba kita buka ya. Coba. Halo?